Hello everyone, I am Priyanka Ghosh, a student of CGEC second year Electronics and Communication Engineering. And today we are going to discuss about classifications of signals and systems. So before moving ahead, we have to know about what is a signal and what is a system. A signal is a quantity that varies with one or more independent variables and represents information about a real world phenomenon. Most commonly, it varies with time. For example, when we speak, the sound pressure changes with time and that's a signal. The voltage across the capacitor changing with time is also a signal. Even an image is considered as a signal, but in that case, it varies with two dimensions, height and width. So, it is called a 2D signal. Mathematically, we represent signals as xt for continuous time signal and xn for discrete time signal. Now, coming to a system. A system is something that acts on a signal and produces another signal. It can be a physical device like a filter, amplifier or a sensor, or it can be a mathematical operation or algorithm. The system is represented as yt equal to t xt, which means the system t transform the input signal xt into an output signal yt. So, the important relationship here is a signal goes into a system, the system processes it and a new signal comes out. The output signal is basically a modified version of the input signal depending on what a signal does. Let's come to the next slide to know about signals a little bit more in depth. Here we can see the difference between continuous time and discrete time signal. A continuous time signal represented as xt is defined for every instant of time. That's why in the upper graph the waveform is smooth and unbroken. Such signal can be commonly occur in nature, for example audio signal, analog voltage or temperature voltage. Whereas a discrete time signal is represented as xn, is defined only at a specific time instant in the lower graph. The signal appears as individual samples shown by vertical lines. Between two samples, the signal has no value. Discrete time signals are mainly used in digital system and signal processing. So now the connection between two is sampling. And now we have to know about what is a sampling. Sampling is a process of converting a continuous time signal into a discrete time signal by taking its value at regular time intervals. This step is essential when real world analog signals are processed by digital devices. So, we can say the summary can be that a continuous time signal are continuous and smooth and discrete time signals are sampled and point-wise, and sampling acts as the bridge between the analog and digital world. Now, coming up to the next slide, we have two more signals called periodic and aperiodic. A periodic signal is a signal that repeats itself exactly after a fixed interval of time, called the period, denoted as capital T. That means if you observe the signal now and then look at it again after time t, it will look exactly the same. Mathematically, this is written as xt is equal to x of t plus t, where t is the fundamental period, the smallest time after which the signal repeats. Common examples are sine waves, cosine waves or AC voltage signals. This repeats again and again in a regular pattern. On the other hand, an aperiodic signal is a signal that does not repeat itself after any fixed interval of time. Even if you wait for a very long time, the signal will not come back to the same pattern. We can take examples that can be signal pulse like a sudden spike or a decaying exponential signal, where the signal gradually decreases and never repeats. So, in simple terms, periodic signal have a repeating pattern, aperiodic signal have no repetition, and this distinction is important because many signal analysis techniques depend on whether a signal repeats or not. So, in the next slide, we have the difference between energy signals and power signals based on how a signal behaves over a long period of time. An energy signal is one whose total energy is finite, meaning if you add up the signal strength over all time, you get a limited value. Because such signals usually exist for a short duration or gradually decaying. Their average power over infinite time becomes zero. That's why energy signals are typically non-periodic and have finite duration, like a signal pulse or a decaying exponential signal. A power signal, on the other hand, continues forever in time. Since it never stops, the total energy becomes infinite. However, when we calculate the average power, it turns out to be a finite, non-zero value. This is why most periodic signals such as sine and cosine waves or AC voltage are classified as power signals. So, the key idea is energy signals have finite energy but zero average power. Power signals have finite average power but infinite energy, and a signal cannot belong to both categories at the same time. So, let's move into the next slide. Here we will simplify it in three different parts: the visual, the math, and the big idea. So, first we will talk about the visual or the graph given over here. Take a look at the blue line in the circle. Notice how it passes through the center, the origin, and looks exactly the same if you rotate the whole image ups and down. This is a classic odd signal. In this specific case, it is a sine wave. If you folded the paper across the vertical line, the sides wouldn't match. But if you rotate it in 180 across the center point, it lands perfectly on itself. Second, we will talk about the rules of symmetry. So, there are two main flavors of signals shown here: even signal and odd signal. So, think of this like a mirror. If you see a shape on the right, you can see the exact same thing on the left, like the letter U or W. The math for this is xt equal to x minus t. And for odd signal, think of this like a propeller. Whatever happens on the right, it flipped out upside down on the left. The math here is x minus t equal to minus xt. That minus sign just means upside down. Let's talk about the big idea. The most important takeaway in the sentence at the bottom is any signal can be decomposed into even or odd parts. This means that no matter how messy or complicated a radio wave or sound signal looks, you can always break it apart into a mirror piece and a propeller piece. It's like saying every number can be made by adding up other numbers. It's a fundamental building block for analyzing signals in engineering. Now that was it for signals. Now we will talk about the classification of systems, analysis of how physical system transforms signals based on mathematical properties and their restrictions. Now let's break down our next slide, which is linearity property. Think of a system as a machine where you put something as an input and get something as an output. For a system to be linear, it must follow two simple rules that together make up the superposition principle. The first is additivity, the sum rule, and the second is homogeneity, the scaling rule. So, if talking about the first rule, if you put input A and get output B, then put input B and get output B. Putting them together, A plus B should give you the sum of their individual outputs. Output A plus output B. No wired side effect or bonus result, they just add up perfectly. Now, second rule is if you double the strength of your input, the output should also exactly double. If you multiply the input by a constant A, the output is multiplied by the same constant. So, if we now look at the big equation shown over here, look at the left side first. We scale two inputs A1 and A2 and add them together before putting them into the system T. Now, look at the equation again and look at its right side. We put them in separately, get the result and then scale and add them. But the result is if both sides are equal, the system is linear. If they aren't, they are non-linear, like a system that squares the input, where 2 to the power 2 isn't just double 1 square. In short, a linear system is predictable. The whole is exactly equal to the sum of its parts. Here, let's talk about our next topic, which is time variant and time invariant system. Before knowing that, what is time invariance? Think of time invariance as a consistency of a system. It basically asks, does it matter when I perform an action? So, the time invariant or the consistent system is time variant if its behavior is exactly the same today as it will be tomorrow. So, the rule is if you delay the input as an hour, the output is delayed by the exactly an hour. But the shape of the response doesn't change. If you look into the equation, it is x of t minus t naught tends to y of t minus t naught. The analogy is a toaster. If you put bread in it at 8 a.m. or 8 p.m., you get the same exactly piece of toast. The system doesn't care what time it is. But in the case of the variant system or the changing system, the time variant is its internal parameter or behavior change over time. The rule is the input depends on the specific moment of the input is applied. The example could be t equal to t into xt. Because there is a t multiplying the input, the gain of the system grows as time passes. We can see the example as an old battery powered flashlight. If you turn it on at 8 a.m., it's bright. As you turn it on at 9 p.m. after the batteries have drained, the light is dim. The system strength changed because of the passage of time. So now let's know about this topic in a summary. If the system formula has a naked t sitting outside the parenthesis like y t equal to 5t into xt, it's usually time variant. If the time only exists inside the xt, it's usually time variant. And here come to my favorite one, causal and non-causal system. Think of this as a look at how systems like computers or circuits handle time. First, causal system. A system where the output only depends on what is happening now or what happened in the past. Why it matters? This is how the real world works. Your speakers can't play music before you press the play button. So from the key phrase real time, we can understand it cannot see into the future. And what is now non-causal system then? A system where the output depends on future input values. So the catch is these are not physically possible in real time if you cannot have a reaction to a button press that hasn't happened yet. Where we can use them? We can use this in offline processing, like editing a video file where the computer can look ahead at the next frames because the data is already recorded. So from the summary of this topic, we can understand that causal means it's only reacts to the past and present, like us living life, while non-causal needs future data to work, which is why it's only possible with recorded data, not in live reality. So finally, we have come up to the edge of our presentation. We have our last topic, which is BIBO. What is BIBO? BIBO stands for bounded input, bounded output. Think of bounded as simply infinite or within a specific limit. A system is stable if you give a limited predictable input, like turning a volume knob to 5. It produces a limited predictable output. The music plays as a steady volume. So, from the visual, we can see that the BIBO stable or the dark bar, this represents a healthy system. No matter how long it runs, the output stays within the blue bar. It never explodes or grows to infinite. Unstable or the gold gray bar, this is a broken system. Even with a small input, the output shoots off to infinite or unbounded. Imagine a microphone creating a feedback loop that gets louder and louder until the speaker blows. That is an unstable system. From the math, we can simplify it. If the input x is kept under a certain ceiling mx, then the output y must also stay under its own ceiling my. In short, we can say if you can guarantee the input wouldn't go to infinity, a stable system guarantees the output wouldn't either. That's all. This was for today. Thank you so much.